Hello, Namaste, Konnichiwa, welcome to Sunny Sensei. In this lesson, we will prove this fundamental equation. Delta x equals Vi delta t plus 1 by 2 a delta t square. This equation is valid only for constant acceleration, uniformly accelerated motion, UAM. I will first prove this using a velocity versus time graph, the graphical approach, and then prove it again using calculus. Let's start by plotting velocity against time. Velocity on the y-axis and time on the x-axis. Here is the plot. At ti, the velocity is Vi. At tf, the velocity is Vf. The acceleration is the slope of this velocity time plot. This plot is a straight line, so the slope or the acceleration is constant. Let me highlight an important point before we proceed further. Many textbooks and teachers assume the initial time ti is 0. But here, we will not make that assumption. We will keep ti as it is. Why? Because in real situations, motion doesn't always start at 0 seconds. By keeping ti, we make the equation more general and more accurate. Now let's continue with our proof. On this plot, for change in velocity Vi to Vf, the displacement delta x is the area under the velocity plot. We can divide this area into two sections. We get a triangle and a rectangle. So, delta x is area of triangle ABE plus area of rectangle ADCE. Area of triangle is half times base AE times height BE. Area of rectangle is length DC times width EC. Now AE equals DC, both equal to TF minus TI. EC is VI. BE is VF minus VI. So we have TF minus TI is delta T. So delta X is from our earlier lesson, we have Vf equal to Vi plus A delta T. So we can replace Vf minus Vi with A delta T. And we have finally, we get delta X equals Vi delta T plus half A delta T square. Let's now prove this equation again using calculus. We already have the velocity time plot. Here is the corresponding position time plot. Position xi corresponds to velocity Vi at time ti. Similarly, the final position xf corresponds to velocity Vf at time tf. At time t, position is x and velocity is v. Velocity v is dx by dt. This is true for any point in time. Dx is viΔt. V can be replaced by Vi plus a delta t. Replacing delta t with t minus ti. Integrating both sides. Left hand side with limits xi and xf. Right hand side with limits ti and tf. Integration of dx is x within limits of xi and xf. Vi is constant, so we pull it out. Integrating dt gives us t within limits of ti and tf. In this term, a is constant acceleration. Integration of t is t square by 2. In this last term, both a and ti are constants. Integration of dt is t. Let me now create some space, and we have replacing tf minus ti by delta t. Using some basic algebra, solving further, finally, we have delta x is Vi delta t plus half a delta t square. We are done. Now to understand this equation further, let us look at a simple problem. From a height of 500 meters, a ball is thrown vertically upwards with a velocity of 20 meters per second. Ignoring air resistance, what will be the height of the ball after 5 seconds? We have a ball. Initially, at time 0, it is 500 meters above the ground. So, xi, or the initial position, is plus 500 meters. I have assumed this direction upwards to be positive. The ball is lifted upwards from the ground, our reference. The initial velocity of the ball is 20 meters per second in the upward direction. So, Vi is plus 20 meters per second. The ball moves up, reaches a certain height, reverses direction and falls back to the ground. During this journey, we have acceleration due to gravity acting on the ball. It is constant at minus 9.8 meters per second square. We are assuming upward direction to be positive for this problem. Now, as acceleration due to gravity is acting in the downward direction, it is negative. We need to find the height of the ball after 5 seconds. TF is 5 seconds. XF is unknown. Let's figure it out. We know the initial velocity Vi, initial time Ti, and final time TF. The final position XF is unknown. The acceleration is constant at minus 9.8 meters per second square. So, this UAM equation is a good starting point. Vi is 20 meters per second. Delta T is TF minus Ti. 5 minus 0 is 5 seconds. A is minus 9.8 meters per second square. Again, delta T is 5 seconds. Solving further, we have delta X is XF minus XI. So we have now XI is 500 meters. And we get XF equal to 477.5 meters. This is a positive quantity. Positive result indicates upward direction. The ball's final position is 777.5 meters above the ground. To better understand the concepts, let's try to solve this problem again using the graphical approach. We start with the plot. Velocity on the y-axis and time on the x-axis. At t equal to 0, the velocity is plus 20 meters per second. We know that the acceleration acting on the ball is minus 9.8 meters per second square. This means for every 1 second, the velocity drops by 9.8 meters per second. So, after 1 second, the velocity is 20 minus 9.8 or 10.2 meters per second. Connecting these 2 points and extending further, we have the velocity time plot. On this plot, at time equal to 5 seconds, velocity is minus 29 meters per second. We can also see that the velocity is 0 at 2.04 seconds. The displacement delta x is the area under the velocity plot. Delta x is the area of the green triangle, half times base of the triangle, 2.04 minus 0, times height of the triangle, plus 20, plus area of orange triangle, half times base of the triangle, which is 5 minus 2.04, times height of the triangle, minus 29. We replace delta x with xf minus xi. Xi is 500 meters, and we have xf equal to 477.48 meters. The results of both our approaches match to the first decimal place. The slight difference is due to approximations in the graph. Before we conclude this lesson, here is a simple challenge. After the ball is thrown upwards, how much time will it take to return to its original position? Try solving it and share your answer in the comments below. If you enjoyed this lesson, don't forget to like, share and subscribe to Sunny Sensei. Thank you and see you again soon.